One more try. Due to interruption, it'll take now 2 hours.
Okay.
Due to impolite interruptions.
2 minutes.
Okay, so secondary nucleation induced by crystal surfaces, a potential mechanism for in situ nucleation and growth of crystal at crystal magma chambers. So in short, so what is the problem and why we came to this idea about the secondary nucleation? So let's start with the problem. So we have, I would say, a great body of the data now, field, textural, and chemical data, indicating that crystals predominantly nucleate and growth in situ, that is directly at solidification fronts. So is it working here? So somewhere here, and there are a lot of publications on this topic. So even I'm talking about this solidification front when there is no liquid, no crystals in the system. So not that kind of settling of crystal, but that this is the case. So what kind of evidence? And I'll just present you 3 lines of evidence from research of my group. The first one, the field evidence. We discovered that igneous layering in the bushwall complex develops on subvertical and overturned sidewalls of potholes. And I hope you agree that that is not the best place for magma to crystallize, for not the place, a good place for crystals to settle. And more so, we have found igneous layering, which develops in so-called undercutting Marianski Reef, these guys. So these are potholes, famous potholes of the bushwall complex, and they have this kind of octopus going into the footfall rocks, and these red guy chromatites develop at the bottom, at the top, basically everywhere, and with the same thickness. So that's one example, and you see that chromites, irrespective where it is, either here on the plane boundary or here on the subvertical or even totally overturned sidewalls, it is still the same thickness and is nicely develops and feel quite happily there, as shown on this particular photo. Especially I'm appraised by such kind of the cases where these undercuttings, they occur 20 meters below the normal position, so entirely in the footfall rocks. And sometimes these guys can be up to 300 meters long, and they have nice chromatites on both sides. And again, that's kind of developing is not really good for the gravity settling. So irrespective of what you're bringing, either you're bringing magma with the individual crystals or that is clusters, they're supposed to settle on the chamber floor, on this in this case chamber bottom of the sills, but instead we have them on both sides, and that's, I think, a good indication of the in situ crystallization. So that was the field evidence. Textural evidence, we looked at the texture of the UG1 chromatites, which is really fantastic in terms of porosity. Just 73 volume percent of porosity in these chromatites. So there's a little bit chromatites actually. And you see there are a lot of empty spaces where chromite may settle, but it doesn't do. It's kind of hanging. And we were trying to understand this. And the reason finally turned out that all chromite crystals, they form these continuous 3D framework of the crystals, self-supporting, and that's why in 2D it looks as if they are hanging. In reality, they're all in the self-supporting framework, and that's why they're not settling to the chamber floor. Of course, such kind of the framework is difficult really to explain by gravity settling, especially individual grains. So that's why we came to such kind of the story where chromatites in the magma chamber forms directly at the chamber floor, just growing chromites grow on chromites, forming these as shown here and forming such kind of a 3D network of chromatites. And such kind of prediction is such kind of growth. There is a strong predictions, and as nicely indicated by Marian recently in her paper. And if they grow like that, so we are supposed to have a progressive change in the size and grain and shape of the crystal. That is the first one to form, then this one, then this one, then that one. And I think that is exactly what we see in our rocks, the way the chromatites grow. So it's consistent with such kind of a successive progressive growth of chromites. And also, that kind of growth predict that there should be a wide variation of chromite size of chromite grains. And again, we see this, although that's quite tricky, because when you look at the photos, you see that all grains are small, and it gives illusion that they're all of the same size. In reality, it's not. So we calculated this from about 500,000 crystals. Godel did this fantastic job, and you see the distribution. So the size varies from 10 to 20 microns to 200, and it's difficult to work with the microns. And so if we upscale it to kind of the silicate mineral, like plagioclase, so we can imagine the rocks which composed of plagioclase of that size, so 0.1.2 millimeter to 2-3 centimeters in the rock, and that's a huge variation. So we do have a great variation of chromites in our samples. And final, so that was field, textural, and chemical evidence. And one of the beautiful example of the chemical of in situ crystallization from my point of view, which was predicted by Grant Cawthon and my postdoc Willem Kruger using portable SRF confirmed this prediction. We just went into the field, made this green, and look at the chemistry of the magnetite in the field. And now several layers, main magnetite layers, basal layer, so several layers showing the same picture. They show this chromite-rich structure right at the base, very rich in chromite. And so that's, and because chromite is, KD is very high, so the first chromite to form is supposed to be very rich in chromium. So basically, we're looking at the time formation of the rock. So it's going like that, starting with the growth nodes, and then finally filling the spaces between with the melt, which is already depleted in chromium. That's why magnetite is low in chromite. There's several other studies related to these nodes on subvertical in the places where we have a magmatic karst, as we call, and they all show the same thing, quite consistent. Nice. So Ian Campbell was the first to come to conclusion to recognize that the crystallization in the layered intrusion mostly happens by in situ, so at the chamber margins. And on a different, he has a different set of observations, which he used to argue for that growth. And there's also, there are some other studies suggesting this, but it is a Campbell who came with the idea to interpret this growth by nucleation of grains at the chamber margins with a process which is called, which he referred as a self-nucleation. Recently, and so basically he was talking, if you have olivine, then the next generation of olivine will be somehow growing on the olivine, and so on. And so olivine kind of induces crystallization. Okay, basically, yeah, it's easier kinetically to grow, for the olivine to grow on olivine. But this was recent paper by Marian, Zoe, and Brian, and I think I strongly recommend to read this fundamental paper. There's a lot of things really there to digest. And the key point which they found that stated clearly that unfortunately self-nucleation is not really a good process to explain what we observe in layer intrusion, because simply kinetically it's much easier for olivine to continue grow like that rather than to form new crystals. And that's it. So we have a problem now. So what to do with all our evidence, field, textural, chemical evidence, which seems to suggest in situ crystallization, while we don't have a proper nucleation mechanism to explain this observation. And so we have a challenge now. Well, one way to just to throw away all our data and forget about them. And another thing is to try to find some mechanism which can explain us this observation. And that is a challenge which I was trying to address. And this is where we come to this idea about the secondary nucleation in industrial crystallization experiments. As I said, 1 year ago, I had no idea about this process, and I talked with a lot of colleagues of mine, just recently with Tony Philpotts, with experiments, asking, have you ever heard about this term? Not really. Nobody heard about this term. And it is understandable because in our textbooks, petrological textbooks, we have only two types of nucleation, homogeneous and heterogeneous. The one, homogeneous, is just about spontaneous nucleation of new crystals, for example, plagioclase from the melt, and heterogeneous is nucleation of crystals on some other crystals, for example, plagioclase on olivine. That's all what we have in our textbooks. And none of these textbooks you can find a word about the second nucleation, not a word. And I think that the paper which I mentioned by Marian, that's the first paper in petrology which really mentioned this process. There's not a word about this process in petrology. And my daughter is working in the steel industry. And I check on her as well. She also has no idea about the second nucleation, despite working in this field with this all solidification, crystallizations, solidification of steel, etc. There's no word in this literature, the steel casting, there's no word about second nucleation as well. And but if we go to another type of the industry, which dealing with the chemicals, with the pharmacy industry, crystallization of proteins, crystallization of foods like sugar, for example, or pigments and dyes, then they have a very interesting process which is called continuous crystallization. And that is where we see that secondary nucleation. Of course, logically, you have secondary, you're supposed to have primary, right? So the primary, we are quite familiar. So that is homogeneous and heterogeneous. That is what is basically in our textbook. That is a primary nucleation according to this classification. Secondary nucleation has a lot of the subtypes, but they are all, the idea is quite simple. So idea is that if you have a crystals, to be exact, if you introduce a seed crystal in the system, then they act as a catalyst for nucleation. And all of a sudden, the chamber, let's call it chamber there, it's full of crystals. So they're basically like that. So you have a clear solution. Then they put two seed crystals, and in a matter of minutes, the whole chamber is full of crystals. So something happens with these seed crystals, which really induce crystallization in the entire chamber. And of course, of great help here, this forced convection, which they introduced by impeller. And nobody knows really what is going there. There are a lot of theories. I've gone through most of them, not all of them, through most of them. And but we can still subdivide them in two major kind of theme. The first one, secondary, this is nucleation due to breakage of the crystals, attrition. So we're breaking crystals, making a lot of fragments, and that results in a nucleation. And the second one is the various processes working at the crystal-liquid interface. Around all crystal, we have a liquid boundary layer, and something happens there which really induces these nucleation. And the first process, they talk about the parental crystal subjected to fluid shear, to collision with the impeller vessels, or collision with the other crystals, when you just break the crystals, and then these large crystals are broken, you have fragments, and these fragments, they acting as a new nuclei. So strictly speaking, it's not in nucleation even, because nothing nucleates. You just have fragments and they grow. So that's why now I see a tendency that people stop really calling even second nucleation, because something else. Because we don't have a forced convection in magmatic systems. So I think that processes are unlikely to work. It's not applicable to our case. But there is another processes, series of processes, where secondary nucleation takes induced by surfaces of seed crystals. And I put here three major models which are most popular now, as far as I understand. That is embryos coagulation, secondary nucleation, this contact-induced heterogeneous nucleation, and secondary nucleation by antiparticle energies. And all this, they're not exclusive. They're just trying to explain what happens in the chamber when you introduce these seed crystals. A different approach, but they're all about the same things. Just to show that these papers are quite well referenced. A lot of references to this paper, mostly in crystal growth design. If we apply the to igneous process, magma chamber, basically they're telling all these three models, they're telling that if you have some crystals, in our case olivine, then something happens at the crystal liquid in the phase which induces nucleation of new crystals, olivine of new generation. So that is not that different from actually Campbell was suggesting, but that's different name, secondary nucleation. So my feeling that these three approach, I don't know which one is correct, and actually I don't care which one correct. The major thing is that if you have crystals, then something happens in the crystal liquid interface which induces nucleation, secondary nucleation. So I think that is can be applied to magma chamber. Why? Because if secondary nucleation is induced by pre-existing parietal magmas, and we know this from these experiments, and we know that in our magma chamber, at least in my magma chambers, we have a solidification fronts with a lot of crystals. So that is logical to expect that is where this second nucleation may really work and produce new nucleus in magmatic system, in magma chambers. So mechanism we developed second nucleation, not actually developed, just drafted. I would say, okay, first of all, on my planet, I live with such kind of magma chambers, with no crystals in the magma chamber, all crystals along solidification front. That's how my planet works. And here we have a solidification fronts with about sometimes zero mass, sometimes a few meters crystal mass. So thin crystal mass here, and the same along the upper margin, and just in front of the solidification front, we have a compositional boundary layer. And I'm going to play now with this compositional boundary layer, and then my next slide. So I use this idea, this model, embryos coagulation secondary nucleation model, to develop this idea. But I can use two other models in the same way to develop basically the same story. And but that story about in the frame of this model, I just like it more for some reason. I don't know why. Anyway, according to the classical nucleation theory, we have embryos in the melt, and there is a little of embryos in the compositional boundary layer. It's depleted around these crystals. And then, which is classical, this model tell us that we have attraction forces, van der Waals forces, which these crystals maybe attract these embryos to the surfaces of the crystals. Or alternatively, these embryos may be physically brought to these crystals if we delete by compositional convection, this liquid boundary layer. So it was here, if we delete it like that, so these all embryos will come close to the surface, and by van der Waals forces, they will be attracted. They coagulate, forming bigger embryos. Now we call it already, we can call it critical nuclease. And then these guys finally may crystallize, may form already crystals on existing crystals. So that is idea how we can do this, and I think we have some potential evidence for this process to work in magmatic systems, because there's the experimental Giada and Steve have a work in progress with the Kilaua basals of that composition at the moment, and adding chromite there and see what happens with the chromite in this system. And they reproduce very nice in the experiments. They see very nice monomineralic clusters of chromite forming in their systems. And you know what is important for these experiments, there is no indication of the crystal settling, so no settling, and there's no bubbles, so there's no advection, and no thermal convection. It's impossible in the experimental test, just because of time, because of the length scale. And so that's difficult to imagine that you can really do this crystals, these clusters form that crystal by kind of bumping of crystals and coming together. It's a process called syneiosis. So no such kind of process. So if not, then there should be something else standing behind this formation of these clusters. And we speculate here that perhaps such kind of the clusters, monomineralic clusters of chromatites, can be produced by secondary nucleation induced by surfaces of the first formed chromite. You form chromite, and then they induces other crystals to form on the existing crystals and produce such kind of monomineralic. And I especially like these guys, which shows how these caterpillars, as Steve likes to call them, caterpillars, this monomineralic clusters, they apparently nucleating on chromites and forming such kind of the I don't know how to call it anyway, clusters. And I like it because that is not that far from, that kind of experiments are not that far from what we proposed earlier in our paper, just from the looking at the texture of the chromite in thin section and in 3D. And take-home message first, I think that secondary nucleation induced by surfaces of pre-existing crystals can be a potential mechanism for in situ nucleation and growth of new crystals and the chamber margins. And take-home message two is that second nucleation is a potential way to reconcile the concept of in situ crystallization of Campbell, which I think is a brilliant idea, for layer intrusion with the basic principles of the nucleation theory. And I will be happy to answer questions. I was reasonably short.
Very good, Ryan. In your experimental picture, it looked like all the chromites were the same size.
Yeah.
All the same size. Let's look.
Yeah.
So the ones near the olivine should be older than the ones at the end.
If you have a big one, then they should get
Yeah,
smaller.
they should. Why don't they? That's
Okay, something to think about.
Other question?
Yeah.
I think Benjamin, did you have, no, Craig, no, Benjamin, you had a big one.
What is kind of the what requires for the chromites to not make a new like overgrowth and rather than the ring rate
Yeah, that's something we need really to think about. There's a lot of things which is not clear to me, but the basic principle. So you know, if we follow idea that if you have a crystals and it always getting just bigger and bigger, so apparently these experiments and the second nucleation experiments in industry show that that's not the case. You may form crystals, new crystals, and not necessary to form just to overgrow the existing ones. What exactly is causing? That's a big question, especially for the magmatic system. Whether it's supercooling, because if you're deleting this liquid boundary layer, so the magma which comes into contact with crystal is supercooled. Whether that's what kind of amount supercooling you need to do this job, I don't know. And you know, we need to have a real experiment specifically studying this process, and whether it's possible or not, I'm not sure.
谢谢。
Yeah.
I have another small question is that even in the industrial chemical experiments and also in this experiments, the connected chromite is freely distributed in the whole system, not just on the bottom, but it's also not just formed on the boundary of the olivine. So it's different from
yeah, because these experiments are not done in the next step we're going to do is to have a unidirectional crystallization. So we have a cold base, let's say, and hot top, so that we have a directional crystallization. Now it's just the same temperature everywhere, so it's not surprising that basically they form everywhere. But it would be nice to have a unidirectional growth, so that instead of one of like that, you will have maybe dozens of these growing unidirectionally from the base of the chamber like that, or crystals. Yeah.
You said the liquid not moving in here?
Yes, yes.
How do these little nuclei get to the crystals?
So why not to form from the liquid which is around these crystals?
Well, then it basically, that gets to my other point.
Yeah.
Why not simply say that a chromite contact has a lower free energy than a chromite silicate liquid?
Okay.
Such that to nucleate on a chromite, even though there's a chromite already there, it actually has a lower saturation point than does chromite against silica, a silicate liquid.
But that was idea by Campbell. I think it was criticized by Marians, saying that perhaps it is kinetically more favorable to grow rather than to form new crystal. That was a problem I was dealing with.
Yeah, but it's growing because a chromite contact has a lower free energy than a chromite liquid contact.
Okay.
And therefore that chromite wants to keep growing. And that's why as you noted in your paper, you get chromite bases in contact more than just chromite just touching each other.
Okay.
Can I just jump in there? The chromite melt dihedral angle is very low. That's 30 degrees. So actually the chromite grain boundary is higher than chromite.
Then why did you said that they could be done formed by solutions when they come together?
Yeah, it's an interesting point. I mean, the point I wanted to make is sort of all joined up with this. So firstly, I totally agree with Dick's point that these grains are all the same size. So that doesn't make sense that the one next to the olivine happens to be older than the others, because you'd have to stop the growth the minute another grain stuck to it. You'd have to stop the growth of the underlying substrate, which I don't think is very likely.
Why it should be stopped?
Because they're the same size. So the ones at one end of the chain need to be older than the ones at the other end.
Maybe they can't grow because what's causing them to grow is the fact that they're against another grain, so they can only grow as big as the grain that they're against.
Actually, can I just jump in? This is really new stuff. We only got this from Giada 1 week ago, so we haven't really had a chance to look at it properly yet. My suspicion is that actually not right size, but what we need to do is to actually do the measurements on the CT, which you can see. So before we get into deep discussions about whether they are, can we just wait for data?
Yeah, fair enough.
Yeah, but Godel will.
We're dealing with very, very small grains, so Van Baal's forces are going to start being important. They might just start getting sucked together.
Might be the key thing.
Yeah.
Peak first and then.
In a real box, are the bigger grains zoned at all?
Yeah, chromite is all equilibrated, is absolutely the same.
You can look at slowly diffusing trace elements that maybe wouldn't equilibrate, like phosphorus and apatite or in.
Yeah, but for chromite, do we have anything we can look at? Not, yeah, unfortunately, and so it's, well, olivine, that's, olivine also fast equilibrating.
But you look at.
Our phosphorus, yeah.
Zone, everything else.
Yeah, by the way, well, that's olivine, which we're also part of the story. We see this all a monomineralic cluster with olivine forming basically in the same way. So maybe that's where we can look, yeah. Yeah, we can look at this perhaps, yeah. Yeah.
My question is, what are the physical and chemical natures of the compositional boundary layer?
Chemical and physical. Not sure what you mean by this. So that's traditionally what is taken by olivine. This layer is depleted in olivine components, and then it becomes either denser or, of course, with olivine it becomes lighter and tend to convect. That basically it.
I take the boundary layer just as the mix of the main magma body and the interstitial liquid.
No, I think no. Yes, you have a crystal which growing and taking components which you need for its growth, and what is left, that is a liquid boundary layer. So that's, as I understand, classical understanding of that.
John, you, John, and even, and then it's the next one.
Yeah. But I think there is another model that can explain the chromite change in this experiment.
Yeah.
That the nanocrystal they crystallize at the same time here, and they oriented attach each other to reduce the surface energy, so that they form a chain. So my suggestion, if you have checked your samples, the orientation relationship between your so-called primary crystals and the secondary crystals.
Yeah. So okay, so you're inclined to think that maybe surface energy stuff which bring them together. Okay.
It's a famous model for the crystal growth.
Okay, let me think of this.
It's quite oriented
attachment.
Yeah, I see your point. I see your point.
John?
A little quite complicated. I mean, in every experiment that you do in a salty system,
Yeah.
you get the process. The olivines that grow during the long duration of the storm.
Yeah.
And when you quench it, you change the undercooling, you grow little olivines all around the edge of the first olivine, they all stick out. That's exactly this process. And it's achieved by dramatically changing the undercooling. You can achieve a change in undercooling either by dropping the temperature or by changing the chemical composition for melt, so that your melt phase is now significantly oversaturated. That affects undercooling. Why is that process not relevant?
Okay, but I guess what you're saying, even looking at that stuff, that's maybe they're not that different in size, these guys. So for what you're saying, to form, why they're supposed to grow like that? So during the quenching, what is why not to be everywhere if it's quenching? Or I'm missing your point.
Yes, that's my point. So in the experiments,
Yeah.
we're not trying to replicate this. I'm just talking, you made it sound like secondary nucleation. It's a phenomenon so rare that you've had to dig into dark industrial literature.
Yeah.
But that occurs in every single experiment. Waving.
Yeah. Yeah. Okay. But
Rice was very kind. He made me feel like I'd done something absolutely genius with my chromite crystal. I haven't. It was first year undergraduate material science, just basically pointing out that the physics of Ian Campbell's idea was totally different. And secondary nucleation, there's an enormous literature in it. It's just that earth scientists aren't generally trained in material sciences, so they don't read. It's nothing new. It's been known about for absolutely ages. So he made it seem as though I did some Newtonian breakthrough. I did.
The way to achieve second nucleation is to observe the system dramatically so that you have changed the undercooling. So the crystal is happily growing at some modest undercooling and it's getting bigger.
Yeah, that's different. That's different because in the experiment they don't do anything with this with the undercooling. They just
That's experiment.
yeah, but
The way of achieving transition from crystal growth to crystal nucleation.
I think
So
it,
there are two sorts of.
I think it's
nucleation.
different.
One's by attrition, where you're stirring it, so you're just breaking off little seeds, and the seed is essentially just a tiny little crystal. It's not actually nucleation. You've got a little bit there. And the other way of doing it is to change the boundary layer. So at the same undercooling, you change the overall conditions because you change the structure or the composition of the boundary layer, and that can then trigger nucleation at the same undercooling. You don't need to change undercooling for technique.
yeah, exactly the same.
You don't need to. But if you change the undercooling, you trigger secondary nucleation.
You can trigger a second generation of homogeneous nucleation.
Not the second, not the second.
Because secondary nucleation depends on the existence of a crystal of the same phase. So primary is when there are no.
You heat your olivines. I can't get the internet, I'll show you a photo. You heat your olivines grown conditions. And then around their surface are all these little needles of olivine that stick out. And that's they're dendritic. And that's secondary nucleation because during that rather rapid. No, it's not.
No, that's not.
It's slightly different meaning.
It's a different.
I see what you mean. It's just yeah. I mean, you change the undercooling, so you're changing. But that's not what Rais is talking about. It's not.
Yeah. We don't need changes.
Isn't it that process? Why is that not?
Because when people are crystallizing things for industrial purposes, they don't fiddle with the undercooling.
But nature fiddles with the undercooling all the time.
But that's not what the literature is about. That he's fitting into.
But I thought he was trying to understand ropes.
So John, you're suggesting that what we're seeing here is sequential.
Yeah, that's.
Well, I'd be hesitant about calling a dramatic change in undercooling a question. There's one way of achieving it. You could achieve it by changing the water pressure. You could achieve it by dramatically changing the chemistry so that your phase that was just saturated becomes now oversaturated. Those are all ways, it's the effect of undercooling.
So these things are growing from massively supersaturated.
Oh, are they?
So it's superheated a kilowatt tholite with an excess amount of chromite, took it up to 1600 degrees to dissolve all of that chromite, and then held it. So it was 1200.
Yeah, 1200.
And this is what you get. And these aren't the products of quenching that experiment because quench chromite looks very different. Chromite falls down. So it's superheated them out and then equilibrated it at a lower temperature. So the reason that works is because chromite solubility is massive. So you can dissolve 10 times as much chromite at 1600 degrees. So that's basically.
So it's a big undercooling.
It's a big undercooling.
Yeah, of course.
But that's what we think is happening in nature.
Okay.
Okay.
Did you have a?
Try to be sure. One can find that there are similar principles which govern intergrowth of chromite in your theory and nucleation and coagulation of sulfide during silica sulfide immiscibility. So is the principle you suggest for chromite growth, for chromatite origin, maybe partially applied to the origin of sulfide deposit by immiscibility and producing some kind of...
Never thought about yet. Never thought. Okay, I don't know. But I think that's we show it for chromite. We have the same thing for olivine. I think it's applied to olivine, but need just to think about if it's possible.
The sulfide liquid is a new phase, and it is also subjected to van der Waals phases and
Maybe. Okay, great. Thank you, Rais.
Ilya is still awake in Russia.
Ilias, not lying on the sofa.
Yeah, I'm still here. I'm enjoying your meeting enormously.
So I guess Ilya will have to share his screen there.